Welcome to our next video for Stat 420. In this video, we're going to talk a little bit about design. We don't spend a whole lot of time talking about design in this class, but it is good to just be familiar with kind of like two general types of design, experiments and observational studies, because the way that the data that we're looking at is collected, whether it be through an experimental setting or an observational study setting, does affect the kind of claims that we can make when we're working with that data. So we've already talked about this a little bit before, but we'll just kind of make it a little bit more explicit in this video. So an experiment is when we're collecting data through a controlled intervention. In other words, we are trying to specifically detect causal effects from one particular factor, one particular variable, onto some other variable, some kind of response variable. So in this case, all factors except for what we're designating as the treatment factor, what we're designating as the causal agent, are going to be controlled across all the different groups that we're comparing. Ideally, we are randomly assigning units or some other appropriate sorting method to ensure that we have equivalent groups to compare. And then the one thing that we change is this treatment factor. So everything is, ideally the same except for the treatment factor. And then if we observe differences in this response, so this response variable that we might have at the end, if we observe differences between the groups, that suggests that maybe it was this treatment factor that is causing that difference. If we don't have a good experiment and we have other uncontrolled factors, some other confounders, as we might say, then it's harder to be sure of causation. Maybe we have to kind of question that or investigate after the fact. But if it's a well-done experiment, we will have evidence of causation if we observe differences in the group results. That's in contrast to an observational study, where here we're just observing variables kind of out in the wild, as you might think of it, because there isn't going to be a controlled intervention in this case. So an example of an observational study might be asking people about, smoking, and maybe we have a question about smoking, and we want to know if maybe there's a correlation with lifespan or some other kind of health aspect. But if we're not assigning people to be smokers or not smokers and doing some kind of controlled intervention with smoking, then we can't exactly make a causal claim all on its own just from this study. Really what we can do is we can find a correlation. We can notice that people who smoke are also more likely to have X or also more likely to have Y, and that is a correlation that we might see in our data. And then we might need to do further investigation to understand if this could be a causal relationship. We could use stratification later to observe differences between the smoking and non-smoking folks to see if there's any other differences, any other possible confounders that might make these groups different and have different responses besides just the smoking. So an observational study, all that to say, it's really only designed to make correlational connections, to note when things go together, but it can't in itself tell us causation without further investigation, theory building, and maybe some other kind of data collection. So I guess I already kind of talked about this already, but just specifics of an experiment is that we have some kind of factor variable. Maybe we even have a couple different factor variables. And what we're doing is we're changing the levels of those factors for each of our experimental groups. So for example, if we're studying plant growth, we might have a factor variable be temperature, and we set temperature to be 60, 65, 70, 75 for our different groups. And that would be like the thing that we kind of change, and then we try to hold everything else constant to see if we get differences in growth. That would be a numeric factor variable, or it's like it's a numeric variable, but we could treat it as a factor variable where we set specific values for each group. We could also have a truly, categorical variable, such as like the color light that you might use. We might have green light, red light, or natural sunlight as different factor levels that we're comparing for each group. We could also, as we'll talk about at the end of the chapter, have multiple of these factors at the same time. So we might have a group that has temperature of 60 with green light, temperature of 60 with red light, temperature of 65 with green light, So we could kind of vary the different combinations of factors and then see, number one, is there a relation with the light level? Is there a relation with the temperature? Should we build a model that includes both of these, or is one of these factor variables seem to be irrelevant to any difference? So again, if all other conditions are equal and controlled, then we can evaluate for whether the differences that we observed would just be random chance or suggesting actual differences, maybe because of the manipulation that we did. However, and this is a little bit above what our course is going to worry about, I'll just kind of mention this. Even when we do an experiment, there are still threats to causal claims that can come up. And here's just a couple examples. So for example, group selection. Is there any reason to think that the groups that I have are not completely equivalent and balanced? Was random assignment used or some other blocking used? And going kind of along with that is you want independence of the units within a group. So for example, I was reading a study the other day that talked about an experiment, and they said that their sample sizes for each group were like 500 and 300. I think it was like a vitamin D study in the relation of treating COVID-19. And initially made it look like the group sizes were 500 and 300 because there's 500 and 300 people. But what was really going on was they were randomly assigning wards to vitamin D treatment or not vitamin D treatment. And they only had 8 wards, 5 of which were assigned to one, 3 of which were assigned to another. So that would be an example where really what I have is group sizes of 5 and 3 with multiple units within each group. So that's kind of a whole nother layer of design consideration that can, make the claims kind of fuzzy and what I really did there. So group selection just has to do with I randomly assigned or did something appropriate to ensure group balance, and that I have enough units there. I have enough independent units to really observe, random variation as it would happen and be able to see what could happen or if the differences I observed are beyond random chance. Setting effects. So for example, are all environmental settings equivalent for each group? A lot of times when we think about people, we also kind of get into the discussion of placebos and the idea that if we have a control group and there's people in it, we want to be careful of the psychological aspect, that people don't feel like they're in the control group, but that everybody feels like they're getting some kind of intervention and that they're being, kind of monitored, that they're part of the experiment, so that everybody's experiences are still the same, even though what they're actually getting might be a little bit different. So that's why you commonly see placebos, is to try to make all the experiences of every group as similar as possible, except for the actual thing you're trying to study. And just any other confounding influences, any differences in the timing of when the groups are completing their experiment, any differences in adherence and people keeping up with their treatment if this is a people study. So there's a lot of things that we can point to that can creep into even experimental designs that weaken the causal claims. So anyway, all that to say, that's just a very brief discussion of design. You can take a whole class about experimental design and learn lots of things. But this is important because we're going to be talking about ANOVA in this section. And ANOVA is typically an analysis used in experimental settings. It doesn't have to be, but it often is. So it's good just to talk about when it's appropriate to make causal claims, why we're doing this, rather than a lot of the data we look at may more commonly be observational study data.